All right, thank you. So OCP LOCK is primarily driven by a consortium of companies, got a couple of hyperscalers and some storage device suppliers. We also have gotten a lot of great feedback from others in the community, so we want to call that out. So briefly, an overview of what we care about storage security. So you have encrypted data at rest. You have media encryption keys, which actually are the symmetric encryption keys for that data. They'll typically live inside the storage device, bound to different users, different passwords, or pins. These credentials protect the media keys, and we rely very much on the fact that there's a cryptographic binding between the pins that you provide to the drive and the actual keys that protect the user data. This lets us establish strong claims about if you walk away with a drive and you don't have the pin, there's nothing you can do to that drive to recover the user data. So some areas of concern and opportunities for improvement in this space. The quality of the encryption implementation. We see some variabilities here, and this is where we don't like to be surprised. We like everything to be boring. The access model for data authorization. If you were in the talk earlier in the storage track, we discussed more about the challenges and opportunities there. And auditing of cryptographic purge. When you go tell the drive to erase itself, did it actually happen? And can you interrogate the drive to decide if that actually did happen? The threat models are rather sophisticated here. So as I mentioned, you could have someone walk away with the drive, and every key left on that device could be exfiltrated through invasive means. You could have firmware compromise, so any keys visible to firmware could escape. You could have keys that were held by one of your customers or one of our customers be compromised. It's our hard drive, it's users' data, and they want to control their keys. We'd like to maintain some baseline assurances of the safety of that data, even if the customer's keys are compromised, which we don't have control over. Compromised storage nodes. When you're actually unlocking drives for use, there are keys that have to be sent to that node so that it can be given to the drive. We don't have very good options today for end-to-end encryption for these keys if you want to hold them on some remote key management service. And erase processes that are prone to bugs. If you go tell a node to go erase all its disks and it falls over halfway through, it doesn't tell you about it, did the erasure actually happen? These are some problems. We like to be able to interrogate the drives and say, did you actually get erased? And that's hard today. So introducing OCP LOCK, layered open source cryptographic key management, built on Caliptra, scoped specifically to storage devices, open implementation at Chips Alliance. This is an umbrella effort. There is the stuff we're doing in the Caliptra side as well as in TCG, because that's where the storage APIs are defined. So things like MEK multi-party authorization and epoch key purge are going to be defined over there. So announcing now that version 1.0 of the lock specification is now available. We're very excited about that. I was the primary editor on this, but it was very much a team effort. So thank you to everyone who provided great feedback along the way. Some features here you'll find in the spec. We have high-level key hierarchy diagrams. We have definitions of transport encryption using a hybrid public key encryption, both post-quantum and hybridized. We have allowances for key rotation. We have state machines for ratcheting keys as you're erasing them through the life cycle of the device. We have state machines for interacting with the vendor's encryption engine. As you're programming keys into the drive's AES engine, how does that actually happen from a hardware layer? And we have definitions of mailbox commands for the storage device firmware to interact with OCP LOCK to actually make the keys go. Just want to highlight one of the things that we paid attention to. This is the access control in TCG Real, something which is now better than it was. Previously, you have a few models for data authorization. You can have the default case where either the user's PIN or the admin PIN can unlock your data, or you can have single user mode where just the user PIN, but no one else can unlock the data. What is missing here is joint authorization. There is no and relationship that's formally enshrined in the spec. You can't say, I must have this key and that one, and that one, and that one, and that one. We now have that with multi-party authorization. It has now been published as a full feature set. So feel free to check that out. And these keys that we're adding in multi-party authorization have end-to-end transport encryption. It supports post-quantum out the door. So we have MLChem 1024, P384, and hybridized for both of those. Some key properties of the OCP LOCK spec. It supports Opal, Enterprise, Key per IO. It's on purpose not opinionated about which variant you're using. Internally agnostic. It hardens the storage devices against leakage of keys. So there are some keys that remain held by the storage device firmware, like pins and whatnot that are provided through the Opal interface. But the actual encryption keys that protect user data, the access keys that are used to unlock the access conditions for multi-party, those are all held exclusively in Caliptra, either in the SRAM or the key vault. And the philosophy of OCP LOCK is we have a bunch of different keys and we're using each of them to bind the user's data. So we have the externally injected access keys. If you don't provide those, no access to data. Even if you know everything else on the drive, you can't get at the data without those access keys. And we also use on-device keys. These are erasable keys held in flash and fuses. These ones are interesting because they allow a new paradigm of cryptographic erasure. Instead of telling the drive to erase and rotate its keys, then asking it, did the rotation happen? You can erase these keys, they stay erased, and the drive is now in a state where it will just tell you, hey, my keys are erased and I'm not taking any user data. And the existence of that intermediate state allows you to have some ratchet points in your control plane saying, I'm not going to let this drive through until it tells me it's actually erased and clean. I'm going to talk a little bit about the media encryption keys. OCP LOCK supports a couple of flavors of these. You can derive a media encryption key from a root secret, or you can generate a random MEK and encrypt it to that secret. Why do we have these two flavors? The derivation path is required for Key per IO because you're injecting keys from the host. There's no encryption. You're not holding the keys locally like you would in Opal. So that's why we have derivation. The decryption path is needed for compliance with common criteria. This is an interesting standard that some devices may be subject to, which is a bit overly strict in how you're allowed to establish MEKs and kind of requires them to be randomly generated. So we have this path. I want to talk a little bit about how we protect these randomly generated keys, because there's some interesting, this is going to be an interesting tale of regulatory agencies measuring the wrong thing. When we generate MEKs, we generate them from a DRBG, as one does, and then we use AES GCM to encrypt. This necessarily involves a random IV at the same time. That IV is problematic because in AES GCM, IV reuse is fatal. Never ever do it. Now, since the IV is only so large, that means if you use the same key too often, you may end up reusing an IV, law of large numbers. And so there are rules around how to make sure you don't do that. Like FIPS requires that if you're using AES GCM, you cannot use a key more than 2 to the 32 times. Now, 2 to the 32 is an annoying number. It's large enough that, are you ever going to hit it? But it's small enough that you might, actually. If you sit in a tight loop and keep hitting that key a bunch, you might eventually hit that. And so you have to do things like keep counters and make sure you don't hit the limit, which is annoying, especially for Caliptra, which doesn't have its own storage where it can keep counters. So to address this, we actually came up with a different construction where whenever you encrypt a message, not only do you generate a random IV, you also generate a random salt. and use that salt to KDF to create a subkey, and that is what you use to encrypt your data. This gives you a margin of up to 2 to the 80 different uses of the top-level key, which if each operation takes 1 microsecond will last you 3 times the age of the universe. So you can now credibly claim, I don't need counters, we'll all be dead and gone before we hit that limit. Now, why is it 2 to the 80? This is where the measuring the wrong thing comes in. So for a given top-level key, since you have 96 bits of salt, there's 2 to the 96 possible subkeys you can make. And FIPS requires that any one of those subkeys you can use at most 2 to the 32 times. This is like, you can characterize this as a balls into bins problem, where you have a bunch of bins, 2 to the 96 of them. You're chucking a bunch of balls across them and finding out how many balls can I shove over before any one of them gets too many balls in it. And the math comes out to 2 to the 128. So I'm not going to explain that math, but you can go find it. So job done, right? We found that if you use the top-level key 2 to the 128 times, then that's fine. You're not going to have any one of the subkeys exceed your 2 to the 32 limit. But this is not the full story. So you have a top-level key used to create a subkey at most 2 to the 32 times. You do the math and figure out that the probability of an IV collision for that one subkey is 2 to the negative 33, which is a very small number. That's great. You're hardly ever going to hit a collision for that particular subkey. But we have a lot of subkeys. You got 2 to the 96 of them. And so how do you figure out how many times you'll have an actual collision? You just multiply them together and find out 2 to the 63. So if you use your top-level key that many times, you're going to get a ton of IV collisions. So 2 to the 128 is a wrong number. It's correct from FIPS's perspective, but it's actually not secure. They're measuring the wrong thing. What you actually want is just how likely is an IV collision. So in this case, since we're doing subkeys, what's the likelihood of that pair, the subkey IV collision? You want to keep that probability really low. And that's a very simple thing to calculate through. Just use the birthday paradox and come out with 2 to the 80.5. So there is the real number. Now, does this matter, like 2 to the 80, 2 to the 128? Like, you're never going to hit either of those numbers. But sometimes it does matter. And so it pays to pay attention to what you actually care about. Over to my colleague, Emre.
Okay, thank you. As just mentioned, like in this MEK generation goes through like multiple flows and it gets complicated. So in hardware side and firmware side, we have different like threat vectors ensuring that the case that firmware is compromised, we are not revealing any info. And to support that, we use Caliptra key vault. And even though we have like multiple keys, those are being stored in the key vault. I want to show over here MEK encryption key. If you follow those interlock flow correctly, at the end of the product, you will get MEK encryption key. Later on, that is being used to encrypt the MEK itself. And why we are doing this encryption? Because like you can generate MEK, and then you can store this MEK in ciphertext form in a non-volatile memory. And the next cycle, next power cycle, you don't have to go through the data state. You can just dictate the MEK ciphertext to, again, obtain the same MEK. For that one, we want to ensure that the MEK encryption key and the MEK stays in the key vault and it doesn't leave that boundary. And as a rule, what we did, only hardware is allowed to read and write the MEK, and they can store in the key vault. And firmware can only ask for the encryption. And let's say that the MEK is generated, it stays in the key vault. Later on, firmware can request an AES GCM encryption to obtain the MEK ciphertext. And the problem starts with AES GCM feature. Encryption and decryption are the same. So hardware cannot tell the difference. So what firmware can do, it can request back-to-back to encryption on this MEK ciphertext, and it can indeed obtain the MEK. So that is like a risk, and we cannot put also MEK into SRAM. To prevent it, what we did, we added additional AES engine, that is Caliptra AES ECB. It is not routed over there for the security. It has an advantage over AES GCM because it can behave differently for encryption and decryption. So we are not removing AES GCM from that flow. What we do, we are adding AES ECB right after the GCM to ensure that the OCP flow follows that route in a way that there will be a difference between encryption and decryption. And that's why there will be a case, if there's a case such that firmware is compromised, it cannot request back-to-back to encryption to obtain the original MEK. Thank you.
That's just one example of the lengths we went to protect the media keys throughout the Caliptra lifecycle. Just to revisit our threat model. Drive theft. Mitigate that by having the off-device access keys be safe. Firmware compromise. Mitigated that by ensuring that no firmware can ever see the loaded MEKs. The customer key management. Mitigated that by allowing us to have multi-party authorization. Compromised storage nodes, mitigated that by having transport encryption for the access keys. And buggy erase processes, didn't get into a lot of the details, but we mitigated that by having attestation be standardization be attestable. So summary, OCP LOCK, strong baseline for storage security, building on the foundations of Caliptra. Call to action to encourage everyone to review version 1.0 of the LOCK specification, look out for implementation later this year. We're now actively working on this. Join us in the storage work group if you'd like to help define the epoch key purge flows. And if you're a storage device vendor, look into integrating OCP LOCK. Thank you.
Thank you.
Hi. Very interesting presentation, especially I really like the math part of this. I have one question. Yesterday only went to the OCP LOCK to understand what OCP LOCK is all about. So a question came to my mind. The main contribution of the Caliptra is basically if you have the key management thing, firmware in the Caliptra, you can extend the dice, basically DP to the key management thing, and you can attest it, right? And also, you are generating the key there, and basically you have separation between firmware and the keys, so that is another thing that you're adding to. So I was just wondering whether we can use it not just for storage protection, for other application also.
That is a great question, and not the first time we've heard this question. I think we actually might have a talk later today about that. In general, we're always open to new ideas and use cases, so always open to hear more about that. We tried very hard to nail the lock use case because we care very much about storage device security, but certainly we could see an expansion of this capability.
Thank you.
Any more questions? All shy? All right. Thank you very much, Jeff. Thank you, Emre. Okay.